Alright guys, we're getting into learning targets 3 and 4. Create an exponential equation given a table or graph, and then describe the features of exponential equations. So we're going to get actually into exponential equations now that we've discovered the properties and how we can write them and how we can manipulate exponents. We're going to talk about some growth, some exponential growth and exponential decay and what that looks like. So we're first asked to consider these two tables, and I've already gone in and written the change in the y's. We change in x by 1 in each of these tables. I notice here in this first table that we change in y at a constant rate. Each time we go up, the difference between the one y value and the next is a positive 5. It grows 5. So we have a constant rate here. And we've seen that before. We've seen that in linear equations. We know that that means our slope is 5. So this is going to be y equals 5x, where we have equations in the form y equals mx plus b, where m is our slope. And we know b is our y-intercept, so that's when x is 0. What do we start at? What's our starting value? Well, if we just follow this pattern back here, we would start at 7. And so our equation here would be y equals 5x plus 7. Okay. Over here, I notice that we don't have a constant rate of change. We go up by 50, and then 75, and then 112.5, and then 168.75. So our rate of change is not the same. We don't have a constant rate of change. But turns out we're going to still see a pattern, but we don't know what that is. We know it's not a constant rate. So let's jump ahead here in your notes and actually look at what this equation is going to look like. This is going to be an exponential equation, and they are in the form y equals a times b to the x. And if you want to rewrite that as y equals a, and then in parentheses write b to the x, because we've struggled with, it's only this term that's going to be taken to the x. Only this number will be taken to the x. It's not a times b and then to the x. It's a times b to the x. Okay, and what is going to end up happening here is a is going to be our starting value, and b is going to be our multiplier. Okay, so we're going to have, instead of a constant rate of change, we're going to have a constant multiplier in exponential equations. So if we look at that, we need something where 100 times this something equals 150, 150 times this something equals 225, 225 times this something equals 337.5. Okay, so we can set up equations to find this multiplier. We know 100 times this multiplier b is going to have to equal 150. So I can divide by 100 on both sides, just do this simply algebraically, and b is going to equal 1.5. And I should be able to look at other examples as well. 150 times this same b is going to equal 225. And if we divide both sides by 150, we end up getting the same multiplier. And that will work with each of these terms. So with any of these rates of change, we can find that our ratio should be 1.5. So b is going to be 1.5 in our equation. Okay, so we're going to have y equals some number, we don't have a yet, times 1.5 to the x power. Okay, so we need that starting value, and in the same way we did in our equation, or in our linear equation, we're going to go back up to where x equals 0. This is kind of like in contagion. We need that 0 cycle. Who started out with the disease? What was our starting rate before we started to multiply? So to do that, we know that something, this a, times 1.5 is going to equal 100, because the next term is 100. So we know that this term, whatever it is, a, we're looking for right now, is going to, times 1.5 is going to equal 100. So I'm going to take 100, or both sides, and divide it by 1.5. And a ends up being, if you want to do that on your calculators, 66.6 repeating, or 66 2/3. Okay, So 66.2 repeating. So our equation is going to be 66 2/3 times 1.5 to the x. So if we write that out, if we look at the expanded form of all of this, what is actually happening here is this would be 66.6 repeating times 1.5 to the 0th power, because anything to the 0th power is just 1, and then that equals 66. This is going to be 66 2/3 times 1.5 to the first power, because 1.5 to the first power is just going to be 1.5, and then that times 66 2/3 is 100. And then what we're going to do is each time we're just adding to that exponent. So this would be 66 2/3 times 1.5 to the second power, to the third power, to the fourth power, fifth power, sixth power, and so on and so forth. So we have that starting term A, and then we also have our growth factor B, and we continue to use that growth factor. That's our constant multiplier. Okay, so let's look at these graphs and also be able to talk about an equation from these graphs. So I see that we start at 0, 5, and then our next nice point here, it looks like we're going up to 1, 10. Okay, so right away on a graph, it's easy to see that your y-intercept gives you your starting value, gives you your a. We're looking for an a times b to the x. So our a is going to be 5. And if I look here, what are we multiplying by? What's that multiplier that gets us to 10? So 5 times what gets us to 10? Well, 5 times 2 will get us to 10. Okay, and if we wanted to continue this in, let's say, a table, x, y, we have at 0, we start at 5, at 1, we start at 10, and then at 2, on this graph, we would be all the way up to 20, because this is 5 times 2 to the 0 power. This is 5 times 2 to the first power. This is 5 times 2 squared. So 2 squared is 4, 5 times 4 is 20. All right, or 5 times 5, or 5 times 2 times 2. Okay, so if we had 3 here, that would be 40, and that would be 5 times 2 times 2 times 2, or 5 times 2 to the third power. So that exponent here is our x. It's our cycle, if you want to think of it in terms of the contagion. Over here I notice that we have a decay, and that's what we call a decrease in exponential equations, because we're not growing, we're decaying, we're decreasing, and we're not decreasing at a constant rate, but we are still decreasing at a constant multiplier. I see right away that we're starting at 10, so we're going to have y equals 10 times something to the x power. Okay, now let's make a table here as well. So we have 10, and then the next nice point is 1, 5, and then the next nice point looks like 2, 2.5. So we have x, y, and 0, 1, 2 gives us 10, 5, and 2.5. And you might see here that y's are obviously dividing by 2, right? But we don't want to think about it as what is happening divisible, or what can we divide each y by. We want to think of a multiplier. So what multiplied by 10 gives us 5? What multiplied by 5 gives us 2.5? Well, we can do that in the same way we did over with the table. We can set up 10 times what, b, equals 5. Well, if we solve for b, 10, and divide by 10 by both sides, then we get 1/2, or 0.5. Right? So we have a constant multiplier. 10 times 1/2 is 5. 5 times 1/2 is 2.5. So our constant multiplier here is going to be 0.5, and you can either write that as a fraction or probably easier to write it as a decimal. Okay, so our equation here is 10 times 0.5 to the x power. All right, and that will give us decay. And that decay comes because our growth, our multiplier, our growth factor, is less than 1. If you think about when we stretched quadratics, that less than 1 came into play a lot. That absolute value is less than 1. So maybe in your notes here we can add that when b, the multiplier, is greater than 1, we have growth. And when b is less than 1, we have decay. All right. So before class, try to write an equation for the table here in exponential form and sketch its graph. So kind of get a nice sketch of what's going on in that function. You don't have to kind of mark it all out. Just draw a nice sketch and give me maybe the y-intercept and a couple points.